In this lesson, we'll be applying our understanding of neutralization reactions to determine the concentration of an acid or a base using a technique called a titration. A titration is a controlled acid-base reaction where one solution has a known concentration and the other is unknown. We add the solution little by little until the reaction reaches the exact point where acid and base are present in stoichiometric amounts, called the equivalence point. So here we have the actual explanation of what a titration is. So pretty much goes through the same thing as I just said. You want to measure out a volume of the acid or base that you want to find out what its concentration is. And then we're going to add small volumes of the other reactant of a known concentration until the indicator changes color. And the indicator is just a dye that changes changes color with pH. And then we're going to use the, quote, magic equation to calculate the unknown concentration. So like I said, indicators are organic dyes whose colors depend on the pH of a solution. This slide shows that the pH at which the indicator changes color depends a lot on the actual pH of the solution. And as we'll see, if you have a weak acid or a weak base, this changes the pH at which you have the neutralization point. So say you had a really low pH at the equivalence point, you might want to pick something like bromocresol green because it changes its color at a pH of 5. If you had something that goes through the neutralization point at a high pH, you might want to pick something like thymolphthalein blue, thymolphthalein, because that doesn't change color until you hit a pH of 10. Typically, what people use is phenolphthalein, which is this one over here, because it goes from, when it's in an acidic solution, it's colorless, and then as soon as you get at all basic, well, it's actually at a pH of 9, but anywhere close to that pH, and it turns turns sort of a hot pink color. This says red, it's more of a hot pink color. So we're going to add, I don't know what the volume is, I have a media clip. We're going to add some acid and some phenolphthalein to the flask. And then we're going to add small amounts of the base until the indicator changes color. And like I said, that'll be about a pH of 9. So we're going to be looking for when the solution starts to turn pink. Whoops, wrong place. So when you're really close to the end point, which is where it changes color, you want to add your titrant drop by drop, because there should only be a 1 drop difference between where it is before the endpoint and where you've actually hit the endpoint. So you can see we have a nice persistent pink color. So the magic equation, it's not really a magic equation. Nobody else calls it this except me. But it is very handy for both doing titration calculations. It's also very handy for doing dilution calculation type problems. So typically what I do is I just say, all right, well, molarity 1, I should read the equation. So molarity 1 times volume 1 is equal to molarity 2 times volume 2. So I set molarity 1 to be the unknown concentration. That's the one we're trying to find. Volume 1 is how much of that unknown concentration stuff that you added to the flask that you're going to use for this analysis. M2 is the known concentration, and then V2 is how much you added doing that dropwise fashion until the indicator changed colors. So for an example, we have 25 milliliters of HCl are titrated with 12.5 milliliters of 1 molar sodium hydroxide. What is the concentration of the HCl? So we know that the unknown concentration is the HCl. So we're just going to leave that as M1. We put 25 milliliters of that HCl, hydrochloric acid, into the flask. So that goes down for V1. we were using 1 molar sodium hydroxide for the titration, and it took 12.5 milliliters in order to hit the end point, or equivalence point. So this tells us that the concentration of the hydrochloric acid was 0.5 molar. So why exactly does the magic equation work? Remember that molarity is equal to moles over liters. So if you take molarity and multiply it by a volume, it will give you moles. And so at the equivalence point, the number of moles of acid are exactly equal to the number of moles of base. And so therefore you have hit that neutralization point. So where you have this stoichiometric relationship where it's exactly equal, that's called the equivalence point. The volume at which the indicator changes color is called the end point, because that's the end of the titration. So here we have a graph. It's going to be it's called a titration curve, and we're going to monitor the pH of the solution as we add sodium hydroxide to the flask. And in the flask, we have 50 milliliters of 0.1 molar hydrochloric acid, and we're going to titrate it with 0.1 molar sodium hydroxide. So first, let's get some starting points. So what is the starting pH of the 0.1 molar HCl? So you do negative log of that, and we get a pH of 1. And then you say, all right, well, suppose I go way past the end point, and I've just got essentially nothing but sodium hydroxide in there. What would be the pH at that point? So it'll be pOH is going to be 1, subtract it from 14, gives you a pH of 13. Now you want to know what the equivalence volume is. And so up here at the top, whoops, oh come on. There we go. So there's our V1, there's our M1, and then here's our M2, and we're looking for what this is, put it down here, is the same thing as V2. So we do M1 V1 is equal to M2 V2. You plug in the numbers, and so 50 times 0.1 is equal to 0.1 times 50. Not real surprise in there. This is just to demonstrate what the titration curve is going to look like. All right, so we go ahead and say, all right, well, it's 50 milliliters. Go ahead and we get the titration started. So yeah, it starts out low, pH of 1. When you get close to that equivalence volume, it suddenly spikes, and then that's when you go through the neutralization point, and then we have just base left over, and so it's going to keep on trending up until you hit the pH of 13. So the way you figure out where the equivalence point is just by looking at the titration curve is you want to go halfway up this spike. And so there's a number of ways you can do it. You can like measure a straight line from there, measure a straight line from up above, and take the midpoint. Usually people can pretty much eyeball it. It's not too bad. And then we say, all right, well, this occurred at 50 milliliters. So if we didn't know what the equivalence volume was, we could use that to find, we could use this curve to find what the equivalence volume was. And then you also notice that the pH at the equivalence point is equal to 7. Now the pH at the equivalence point is a good indicator of whether you have a strong acid or a strong base, or a weak acid or a weak base. So the only time it's equal to 7 at the equivalence point is when you have a strong acid, strong base titration. So here we have a comparison between the weak acid and the strong acid. So here's the, let me do a different color. So here's the midpoint for the red curve, and we can see that it is at 7. And then we go to the midpoint of the blue curve, and it looks like it's about right about there. And yeah, it's above 7. So the thing I usually tell my students is that weak acids behave as though they are less acidic. So everything is pushed up on the pH axis. So there's our equivalence volume. So we can see that it went through the equivalence point at 25 milliliters. And the pH looks like it worked out to be exactly 9. So the key things to remember there is that the pH at the equivalence point for a weak acid is greater than 7. The other part, and this is kind of like extra information that you can extract from it, is that if you go to 1/2 that equivalence volume, I've got to change my color back. So it's 25, so that means it's going to be 12.5, which is right about there. And then we find the pH at that equivalent at that point. That pH is actually equal to the pKa of that acid. So remember, the way you can undo the little p function is it's going to be, the Ka is going to be equal to 10 to the negative pKa. So you do 10 to the negative 4.9, hit equals, and it tells you that the Ka for this particular acid is 1.3 times 10 to the minus 5. So it's just extra information that you can get. So here's a comparison between a strong base and a weak base that are being titrated with a strong acid. You would never do a weak base and weak acid titration because the equilibria that are involved will make your curve really messy looking, and it'd be hard to extract any information from it. So we have the equivalence point marked for the weak base. Notice that its pH at the equivalence point is below 7. So again, it's kind of like a weak base is less basic than a strong base, so everything gets pushed down on the pH axis. You can also extract out what the Kb is, but the math for this is a little bit more complicated because pH is all about what the acid is doing. So if you're talking about a base, you're going to have to find pOH and go backwards to find pH. So we'll just kind of just back burner that for now and just say, all right, so I know that it is possible to extract extra information. All right, so the next part of this particular lesson is to talk a little bit about buffers. So if you notice, when you are titrating acetic acid, which is a weak acid, and you could actually tell that this is a weak acid because the pH at the equivalence point is above 7. And we see that even though we're adding lots of sodium hydroxide, we go from 5 milliliters of sodium hydroxide almost all the way up to 25 milliliters of sodium hydroxide. And the pH really hasn't changed that much. And that's because we are actually forming a buffer that is helping to control the pH or limit the amount that the pH will change of this particular solution. So we can look at a titration curve and define a buffer region, but we know we have a buffer. And so the pH is going to be plus or minus 1 unit around the pKa of that for that particular acid. So just to write it out. Oh, my trackpad is not being friendly tonight. So the Ka for acetic acid is 1.8 times 10 to the minus 5. So pKa is 4.74. So we're going to have plus or minus 1 unit around that pKa value, that where it's going to the solution is going to be buffered. All right, so buffers are defined as being solutions that resist changes in pH. The way they do this is by being a mixture of either a weak acid and a salt of its conjugate base. So in the case of acetic acid, it would be acetic acid and sodium acetate, or a weak base and the salt of its conjugate acid. So an example there would be ammonia, NH3, and ammonium chloride. And as I said on the previous slide, buffers will maintain a pH that is within plus or minus 1 pH unit of their pKa. And so this is where it actually goes through all the calculations. So we have pKa of 4.74, so that means the buffer zone is going to range from 3.74 to 5.74. So an important buffer example takes place in the human body. The pH of blood must be maintained at 7.4 plus or minus 0.2 pH units, or death may occur. So that's a very small pH unit. So you actually need a pH range. So you actually need a combination of buffers in order for this to work. So there are two main buffering equilibria. We have the carbonic acid hydrogen carbonate buffer, or equilibrium. And so we can see that that's going to buffer around a pH of 6.4. So we're still way too low. And that buffering system comes from the dissolution of carbon dioxide into your bloodstream. And then the other one is the equilibrium that exists between dihydrogen phosphate and hydrogen phosphate. It has a pKa of 7.2. So that's getting us a little bit closer to that 7.4. We're actually with it at the bare bottom of that range. The rest of the buffering action that we get is from proteins and other substances that are in the bloodstream. And they get it into that last range. So if you ever hear of somebody that has gone into respiratory failure and then they die from that, it's not because they weren't breathing, it's because they're not breathing properly. And so they're not being able to expel that carbon dioxide from their lungs. So we have too much hydrogen carbonate dissolved in their bloodstream, and the pH of their bloodstream drops, and it gets outside of that safe zone. So, for example, what is the pH of a solution containing 0.2 molar dihydrogen carbonate and 0.4 molar sodium hydrogen carbonate? And so remember, the sodium is a spectator, so we don't really care about that. So there's our equilibrium expression for this one up here. We fill in the numbers that we know. So we know that the hydrogen carbonate is 0.4 molar. We know that the dihydrogen carbonate is 0.2 molar. Solve for the hydrogen ion or hydronium ion concentration. And we get that that is equal to 2.15 times 10 to the minus 7. So we know that the pH is going to be somewhere close to 7 because we got that power on the 7. So we end up with a pH that is equal to 6.67. All right, so that's it for the new materials. So the wrap up for titrations and buffers. Buffers are just taking advantage of a neutralization reaction in order to, did I say buffers or titrations? Titrations is what I meant. To determine the concentration of an unknown acid or base. An indicator signals the endpoint by changing color when the pH changes at that appropriate range. Remember, we want to pick an indicator that changes color close to where we're going to go through that equivalence point. The equivalence point occurs when the moles of the acid are exactly equal to the number of moles of base present, because that's where they got neutralized. And then we can look at a titration curve and see when we can look at where the equivalence point occurs. Remember, that's going to be halfway up the spike in the pH values. So we can get the equivalence volume by looking at what volume it occurs at, dropping down to the x-axis. And if we have a pH that is equal to 7 at that equivalence point, then we know we're doing a strong acid, strong base titration. If our pH ends up being above 7, then we know that we have a weak acid, strong base titration. And then This one doesn't show it because this is actually an acid titration. But if you had the flip where it starts out high and then drops down, we could use the pH at the equivalence point in order to say whether we had a strong base or a weak base present. If it's a weak base, then the pH at the equivalence point is going to be less than 7. So buffers resist changes in pH, and that's because they consist of mixtures of a weak acid and its conjugate base, or a weak base and its conjugate acid. The reason why that helps it resist changes in pH is because if you add a base to a buffer, the weak acid is going to react with the base that you just added. If you add an acid to a buffer system, the base is going to react with the acid that you just added. All right, so that's it for this lesson. Thanks for listening.